Okay, let's go over the Lucas Canary tracking. Now, as you guys know that for this project, Lucas Canary tracking will be the only tracking that you guys will have to do for getting the credits for this project, and the MB tracker will be extra credits for this project. So it's optional. So if you want extra credits, you can do this. So I will only go over Lucas Canary tracking. And if any of you guys are interested in MB tracking as well, then you can attend one of our office hours to get all your doubts sorted. Because it is very much similar to Lucas Canary tracking, and we only have a few things that we need to look after. Let's get started then. You have this LK demo MATLAB file. Okay, so this will be the starting point, and you have been given an ROI. So it is 160, 120, 300, and 260, which defines x1, y1, and x2, y2. So you have, keep in mind that all of these are coordinates. It's in the format x1, y1, and x2, y2. And we have a video writer. So all this is done for you. They calculate the width, they calculate the height, and you can also look at the images as you get into the loop. So they extract the previous frame and they extract the new frame. And this is something that I have added to my code, because we need a rectangle of the format XYWH instead of x1, y1, and x2, y2, because the Lucas Canary tracking is expecting a rectangle of this format. And therefore, if I were you, I would simply use rectangle and create very much something like this one that they have already used to send it in. So this has not been done. So keep in mind that the rectangle that is being sent in this particular code, which is not modified, has x1, x1, y1, and x2, y2. So you don't have the width and height that the Lucas Canary.m is actually expecting. Okay, so this function is expecting a rectangle in this format. Therefore, I have created this very much similar to what I have done here. But if you're doing this, you must also remember that you can see that the tracker is actually getting updated here, right? So we have tracker of 3 and tracker of 4. So therefore, the width and height continuously keeps changing when we loop over this particular, when we iterate over this loop. Okay, so width and height calculation should be inside the loop so that we have an updated height and width. Okay, so that's all the change that you need to do in this particular file. If you want to change it inside the file, that is fine as well. I mean, if you want to send this tracker directly inside this particular function, and then if you want to make changes within your function lucascanary.m, you can do that as well. It's up to you, but this is my design choice. So it's just subjective, not a problem. Okay, let's get into the actual Lucas Canary tracking. So what I have done for you guys is that I have sections which will define what you will be doing in this particular section. Okay, so let's say for this, in this particular box, I say that you have to convert both images to double. So this double percentage marks will define the section, and each of the percentage mark as a comment, just replace them with your code. If there are 2 percentage marks, it means that you only need 2 lines of code, not more than that. Okay, and to reiterate that, in this particular box, you have one section that is extract template. Okay, and you have one mark with a comment which you need to just remove this comment and add 1 line of code. So this particular section will only need 1 line of code. Again, this section will need 2 lines of code. This again 1. In case if I need more explanation, what I do is I simply put this this kind of a box. Okay, So if it is inside this, it means that you can simply remove this and there's no code that is going into inside these, percentage marks signs. This is just for making things easy for you. Okay. So let's say if I have a percentage mark here, it means that you have to initialize something here. There is a line of code that is going in this position. If it is something like this, just remove this. That's not a problem. Okay. You can remove this and just start working on your code. These are all just simply to help. Okay. So let's get started. So IT and IT1, as you know, are previous image and current image respectively, and the rectangle is of the format XYWH. That is what this is expecting, and it has to be in that format. In case you're sending X1, Y1, and X2, Y2, make sure that the first thing that you do is change this rectangle into the format XYWH. That is the first thing. And you can see that in the demo video, we have not converted any of the images into double. Okay, so all of them will be in the uint8 format, and it's not a good idea to work on uint8. So always convert the images to double. Okay, so that is why we are converting it to double. So section 1 will simply convert it to double. I hope by this time you guys know how to convert it. So there's just 2 lines of code, one for each image. Okay, now we have to extract the template. So the template means that whatever image that is within the bounding box. So when you run this video, you will see that there's a rectangle that is being plotted on the image, and we want that part to be cropped out. And we call that the template of the template or reference block or whatever you want to call it. So we want to so either you can do a manual cropping. Okay, so you can have IT something like this. You can do something like, so IT of, let's say, X1 to X3, comma, Y1. So this is X2, right? X2 or Y1 through and Y1 through Y2. So this is how you can manually crop it. In case you're sending it as width and height, you just have to do X1 plus width, plus width, and Y1 through Y1 plus width. So essentially we are starting from X1 till X1 plus width. That is the end of the column where we have the rectangle. That's it. Okay. And similarly for the height. So this is how you do manual cropping, or you can also do IM crop, which is very simple. So you just have to call IM crop of IT, rectangle if it is in the format XYWH. So I leave up to you guys to decide whichever you want. Okay. And let's initialize in the next section. We are just going to initialize P and delta P. You know that Lucas Canade makes an assumption that we already have a good guess on P, right? So P is basically a small change in the position of the pixel. So 0 is always a good guess, because when you have a very high frame rate, the movement of the object inside the image from one frame to another frame is negligibly less. So therefore we can set it to 0, which is a considerably good guess. It's not a problem for us. And delta P, it's not a good idea to initialize it to 0, because we have a multiplication factor that is coming in, right? So where is it? Okay, so okay, in this calculation, we are not using the multiplication factor, but if you want to calculate delta I into Jacobian into delta P, then we will have, then since multiplication is involved, 0 is not always the best option. But I think in this, I'm not using delta P as a multiplication factor, so you can initialize it to 0 or 1, whichever you want. But remember that when you have a multiplication, it's not a good idea to initialize it to zeros. Okay, that's one thing. Okay, so only 2 lines of code in this section. And let's go to this one. We have to find the gradient of the current frame. So remember that I will be referring to current frame for IT1 and previous frame for IT. Okay, so that is the convention that we will be using, because that is what we have used here as well, right? So we are sending previous frame and the new frame. So you want to call it new frame or current frame, that's up to you. So I'll be referring it to as current frame. Okay, so in both direction, we have to find out the gradients. So you know that there is already a gradient function in MATLAB, and you have used this before. So this requires just one line of code. Send the current frame into the gradient function and get its gradient ix and iy. Okay, so that's all. So this is all the initialization parts. Okay, so and now let's go to the iterative alignment. So inside, when I say iterative alignment, obviously we need a loop in which we perform a few things, and until certain conditions are met, we are going to continuously iteratively do the alignment. Okay. So what are you trying to do inside the loop? Why do we need loop at all? Is because you're trying to minimize a certain quantity in a particular function. So that's all we need to do. We need to know about it. So for now, let's forget what is that and everything. So we are trying to find a minima in a particular function, right? There's a good chance that you might get lost in, or you might get stuck in a local minima instead of the global minima. It means that your p value, the delta p that you're trying to minimize might not change at all over n number of iterations. So it can be the same value in the 10th iteration, and it can remain same even after hundreds of iterations. So the loop will never come out unless you push it outside, unless you have to force the loop to exit based on certain conditions. So you cannot have just delta p as your loop condition. So we have to have a max iteration threshold as well as a constraint, so that we can come out of the loop when we are stuck in a local minimum. Okay, so for that case, what we'll do is we will initialize a counter. Let's say count is equal to 0, and we'll initialize a max counting threshold. For example, let's say the maximum number of iterations that I want to go is, let's say, 100 iterations. You can choose anything that you want, but just make sure that it is easy for you to debug, because Lucas Canary is an extremely computationally expensive algorithm. So sometimes I use 10 and 20 number of iterations just to make sure that the algorithm is working when I'm debugging. I don't want hundreds of iterations while I'm debugging, because I can't sit and wait for that. So sometimes 10, sometimes 5. It's up to you to use what is the maximum number of iteration threshold that you want. Okay, so initialize the counters. Okay, again, when I have this 1%, it means that only one line of code. So when I say initialize counter and maximum threshold, so what I usually do is I usually do it in a single line. So for example, I can just make it count is equal to 0 as 1, and max count is equal to 10. So something like this. You can do it in a single line. Although it is two lines, you can simply do it in one line. Right. Okay. So we have two variables coming in. Okay, to make it more convincing, I'll just put it like this: initialize counter, and let me make this initialize a max threshold counter. Okay, and now we have to start the loop. So the choice of loop is up to you. So you know that we don't have an iterator inside the loop. So for me, the obvious choice will be a while loop. It's up to you to use whatever you want. And delta p is a vector. So you know that we have initialized p to be a vector and also the delta p to be a vector. So how do you put a threshold on delta p? So you want a scalar, right? You can't compare a vector to a value. So you want a scalar. So what you can do is you can consider the norm of the vector and then use a threshold. So you can have thresholds, if you are very stringent and if you want to have very good accuracy, then you can go as low as 0.1 or 0.001. But trust me, that won't work for you unless your algorithm is exceptionally good. So 1 is not a bad choice for, at least while debugging. 1 is a pretty big threshold, but it's not a bad choice for debugging. So while you are working on your code, just maintain a high threshold or maintain a very low threshold. When I say very low threshold, it means that you give a very high error margin. So it's okay to have the norm of delta p is equal to 1. Typically, you would expect it to be very less because you want a minimum deviation, but it's okay to give a bigger value because we want to work on our code faster. So 1 is not a bad value here. And so try to give a higher threshold for delta p and a very lower threshold for maximum number of iterations, at least when you're working on your code, so that you can work much faster. Okay, so the first thing is, if you're not inside a for loop and if you have chosen something like do while or while, it's always a good idea to increment the iterator. You should never forget incrementing the iterator, because otherwise forever you will be stuck in the loop. So increment the iterator, okay? Then initialize the warp matrix, that is W. So you guys know that it's already given in the lecture. So this is the warp matrix that we're looking at. So P5 and P6 are translation, P1, P2, P3, P4 are affine transforms. So basically we have a 3x3 matrix. It can be a 2x2 matrix as well, but here we'll go with 3x3 because you have to do certain matrix multiplications, and that's why we need a 3x3 matrix. Okay, so there's no line of code going here, but you will need one line of code in this particular part where it looks exactly like this, but you just have to make sure that you're getting it from this P and not simply P1, P2, P3, P4. And also, it's not a good idea to initialize P1, P2, P3, P4 like this. Okay, I hope you guys know that. So just initialize all of them to zeros in the first, in line 12, and then access them through P of 1 and P of 2 and P of 3, and then initialize the W vector. Okay. Now, next question is, the next step is where we have to apply the warp on the image. Now, I had a couple of students who came to office hours, and even I got confused at that time. So, but let's be clear here. We are applying the warp on the current image. So we are applying the warp on the current image, that is IT1, so that we are trying to see how is our warp going to get affected in the new image. So if you open this function, so you can see that it has a T form. This function is already given to you. You don't have to work on this one. This is already there. So it is expecting an image. It is expecting a homographic matrix on which will be applied on the image, and it is expecting what is the out size and a fill value. So for now, forget about the fill value. Fill value is automatically filled for you. You don't have to worry about it. So the idea, if you look at the equation, it makes logical sense to think that you apply the homography on the previous frame and try to get to the point where it is in the current frame. So you have a template that is defined in the previous image, and now you want to get to the current image using the homography, right? So that is how logically it makes sense. But what we are trying to do here is we are going to apply that homography, that is the warping, on the current image and check if it matches with the template. Essentially, we are doing the same thing. So the point is, we don't know what the warp is, right? So we don't know what this is. If we knew this, if we already knew this, then applying to the previous image and getting to a point where it is in the current frame makes sense. But we are trying to find this, right? We are trying to find this. We don't know what P1, P2, P3, P4 is. So we will assume that we know, and we'll apply that on the current image and check if it is right. That's what we are trying to do. So we will apply on the current image. So warp H is expecting 4 outputs. Forget about fill value. You don't even have to send it as an argument, because if it is empty, automatically it will be filled. So let's just send in 3 values. One is IM, that is the current frame. Second is the homography matrix, which means that here it is the W matrix or the warp matrix, and the out size. What is the size that we need, right? What we will do is we will send the size of the image itself. Let's apply it on the entire matrix, and later we can crop it. Because before cropping, if you do a cropping before that, if you send the outsize to be the size of the rectangle that you have, that is the height and width of the rectangle, then it might be possible that you won't be getting the right answer because of the way in which the interpolation is taking place in the IM transfer. So let's make sure that we have homography applied on the entire image. Let the outsize be the size of this image itself, and then later on we will crop it. Okay. So we'll do the warping on the current image, and we'll just crop it to the size of the template. So size of the template, you already know, you're already getting it from rectangle, that is width and the height. And again, when I say crop it, you can do manual cropping or IM crop, whichever is easy for you. Once we have done that, we have the template image and the cropped warped image that is coming from this line 52. So we'll find the error. So basically that means error will be equal to template minus your cropped warped image. Okay, so this is what we are looking at. Okay, and it's not a bad idea even to take the absolute value of this, because it does not matter. But since it is given in the lecture, we will consider the absolute value. Okay, so that is the error image. So error image will be using it while we are calculating delta B. While we are calculating delta P in line 70, and we'll get back to that. Okay, and now there is one step that is missing in the lecture, and as well as in the project PDF, is that you have to warp the gradient of the image as well. So now we have the gradients calculated from this section, right? So we have X and Y both directions, gradients in both directions for the current image. Those also have to be warped just the way we warp the current image. So the gradient should also be warped. So what we will do is we will just call the warp fetch function with the size of the image with the but the only thing is, in this place you have to send in the IX and IY images, and outsize will still remain the same because gradient is not going to change the size of the image. So we will warp the gradient, we'll crop it out to the size of the template. Again, we will warp the gradient in Y direction and we'll crop it out. Okay, and then we find the Jacobian. Let me just get to the equations here for 1 second. So what we are trying to do here is we are trying to find delta I into dou W by dou P. So this is what we are trying to get to. Okay, so this is our A matrix, which is this is the fundamental unit for the A matrix. So if you think of A is this one. Okay, so first we need to calculate this part, right? So only after getting this will we have okay, it's not updating. I'm actually writing on my iPad and hoping it to get synced as soon as I write, but it's not getting sent. Okay, anyway, so you have the delta I, okay, got it. So you have the delta I dou W by dou P. So this is what we are trying to calculate right now. Okay, so this is delta Ix and delta Iy multiplied by dou Wx by dou P and dou Wi by dou P. This is what we want. And we already have these calculated for us. Okay, this has to be warped and cropped. Okay, and we have already done this part. And this is the Jacobian part. And this is the place where it gets really ugly, in terms of mathematics. So what we will do is we'll write another function altogether for this particular function, for this particular calculation. Okay, and I'll explain that as we go ahead. So right now we'll simply assume that we already have this Jacobian. Okay, or shall we do it first? Okay, let's get into Jacobian. Okay, because otherwise you might not be able to understand how this is coming from. So what we'll do is we'll just write one line of code which says my j is equal to get Jacobian of width and height. Okay, I'll explain what width and height is and where is it coming from. So this is simply one line code function that we are going to write, and that comes here. Okay, although this is not given in the lucascanade.m and your function ends here, I suggest that you write another function altogether just to create the Jacobian. Okay, now we need to get into the theory a little bit because understanding this is not so straightforward. Okay. All right, so we have dou wx by dou p, and okay, so we already have this already explained in the lecture. You guys have seen this in the lecture, so let me just get that. So you have already seen this in the lecture. X0 y 0 1 0 and 0 x 0 y 0, right? So the question is, where is this x and y coming from, and how do you apply to each and every pixel? Because if you consider delta ix into delta iy into this matrix dou w by dou p, okay, so the question is, this delta ix is an image, okay, delta iy is also an image. I'm sorry, it's not getting synced, but it'll come. Yeah. So we have delta ix to be an image and delta iy to be an image. And this image is of the size w by h, and this image is also of the size w by h. But dou w by dou p is a 2x6 matrix in which x and y are pixel locations of every pixel in delta x and delta I, right? So if you look at it in a big picture, you might not understand how these things are working. So how can you get Jacobian? How can you multiply an image with a 2x6 matrix? So this can get a little ugly. Okay, so what we'll do is we'll try to understand how images work now. So let's say we have two gradients. Okay, so we have delta ix and delta iy. Okay, and both of them have the width w and both of them have the height h. Now dou w by dou p. Okay, so let us take the very first pixel. Okay, so let me call this delta ix1. Okay, delta ix1 and delta iy1. That means I'm referring to the first pixel multiplied by x0, y0, 1, 0 and 0x0, y0, 1. Okay, now it makes sense because this is just one value. So basically when you take just one pixel, this is just 1 cross 2 and this is just 2 cross 6, and we already have, we can do a multiplication, correct? And this x and y is nothing but the location of this pixel that you have obtained from your template. Okay, so this is not a big issue. Does it mean that you have to do it for every pixel of this image? For example, let's say, how many number of pixels do you have here? So basically you have w into h pixels, right? So if you start, so now you see where Lucas Canade is getting extremely computationally expensive. Now I have to do this particular matrix multiplication, that is delta ix and delta iy into dou w by dou p for every pixel. And if I have w cross h pixels, then I have to loop it so many times just to get to the multiplication, correct? So the complexity here becomes O of W into H. So that is the complexity we are looking at. So this is where Lucas Canary becomes extremely computationally expensive. So now what we will do is we'll start vectorizing equations. So what do I mean by that is you have, let's just consider delta Ix. Okay. So now delta Ix, for simplicity, I'll draw a 3x3 matrix. Assume this to be an image, okay, with height is equal to 3 and width is equal to 3. So now let me also name the pixel 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay, so whatever I'm speaking might not be exactly syncing with what is coming on the screen because I'm writing it on a different device, but just bear with me, okay? Now, I want to consider delta Ix to be a single column vector, okay? So that is in MATLAB, I can use delta Ix of colon. So this will vectorize for me, okay? So delta Ix, this will vectorize it for me and give this image as a single vector. But when I do that, how is it going to do? That's the question, right? So I get it as 1, 4, 7, 2, 5, 8, 3, 6, 9. This is how the image is going to be, right? Okay. I'm hoping that it gets updated soon. Okay. So it means that I have a single column vector, okay? But so now you can see how many columns did I stack now? So I had to stack this here and this somewhere here after I got 2, 5, 8 here, right? So this is how I had to stack it. It means that I am stacking each column of X W times, right? So I am stacking 3 times so that the vector, the column vector, the length of this column vector is basically how much? W times 1. So this is the overall length of this vector will be W comma 1, or so basically height into W comma 1, but I want to repeat this 3 times, right? So I'll consider this to be once and this to be twice and here this to be thrice. All right. I know this can be a little confusing. Okay. Now let's understand why. Okay, delta Iy. Let me draw another matrix here. Okay. But now I'll just change the naming convention. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Now, if I try to vectorize this, I'll get 7, 6, 3, 8, 5, 2, 9, 4, 1 as my output, right? But now what we have to make sure is since we need X and Y to be corresponding to each other, that is when I have 1 from delta Ix, then I should have 7 from delta Iy. And when I have 2 from delta Ix, I should have 8 from delta Iy. Okay, if you understand what I'm telling. So you have to have a correspondence. So if I simply concatenate, if I simply try to vectorize this delta Iy, okay, the corresponding is missing, right? So 1 and 7, of course, they correspond to each other, but oh yeah, actually it's not. So you have this correspondence, right? So I can simply stack these 2 vectors together. So I have delta X and delta Iy. So now what is the next thing that I can do? So I can have delta I to be equal to delta Ix stacked as a column and delta Iy stacked as a column, right? So when I have this, I can easily create this part for the entire image. So we have created this particular part for the entire image. And you know what is, you already know what is the length of this particular delta I. So delta I will have the dimension W times H because it is so many pixels that we have. And the number of columns is just 2 because one is for delta Ix and one is for delta Iy. Okay, all right. So now we have figured out how to vectorize delta Ix and delta Iy. Now what we have to figure out is how to create dou W by dou P. Okay, so this is what we are trying to figure out. Now, okay, let's come back to this one. So you know that while you're vectorizing, you're taking one from Ix, and then, so the way you're traversing in order to find, so now we have to find for all the pixels, right? So how do you traverse? So I have taken one pixel number 1, that is the first box in the delta Ix, and 7 from delta Iy, correct? Now, what is the location of this? This is 1, 1, right? This is 1, 1. This is 1, this is 2, 1, and this is 3, 1, right? And here it is 1, 2, 2, 2, and 3, 2. And here it is 1, 3. And here it is 2, 3. And here it is 3, 3. Okay. Similarly for Y, this one is 1, 1. This one is 1, 2. This one is 1, 3. And here we have 2, 1. This is 2, 2. And this is 2, 3. I'm just going to tell you why this is very important. And here we have 3, 1. This is 3, 2. And this is 3, 3. Why this is important is because we have to decide x0, y0, 0, 1 and 0x0, y01 for the dou W by dou P. Now, if you look at this, we are stacking all the x at once, but we are not stacking the y in horizontal way, right? We are stacking even the y's in the horizontal way. So now I cannot simply, so in dou W by dou P, how do I take this x0, y0, 1, 0, and 0x, 0y, 0, 1. So now how do I stack this x so that all of this can multiply together? I have to multiply the entire thing here, right? So how do I do it? So I need to create an x which is of the size w, h. Sorry, start the way around. H, w. I have to create a y which is also h, w, because I have to consider every location, correct? So I have to have x and y's for all the locations, because if you look at the equation, let me write the equation again. You have delta Ix, delta Iy multiplied by dou Wx by dou P and dou Wy by dou P. I know this is very confusing. I understand that this is confusing, but you have to bear with me to understand, okay? So now what I'm trying to tell is this dou Wx by dou P has this particular form, right? The first row. And dou Wy by dou P has the second form. And you should observe that both first row and second row has x, y for each pixel. Therefore, this alone, that is the first row alone, this guy alone has an X of size W cross H and Y of size W cross H. And this guy alone has an X that has size W cross H and Y is equal to W cross H. So each of them is equivalent to an image because we have to calculate for every pixel. Okay, so now what we are going to do is, let's come back to the code. Okay, so now we are going to create a column vector for X is equal to 1 through W. So what does that mean? Let's create X is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9. No, let me just consider only 1, 2, 3 because we only have. I'm considering this as an image right now. Okay, so my image is this, and we want the locations. So when I say the location, it is not the 1, 2, 3, 4, 5, 6, 7, 8, 9. They are the intensity values. The locations are 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, and so on and so forth. So now if you see that in the X direction, we have 3 columns, right? So 1, 2, 3, we have 3 columns and H is equal to 3. So that is, we have 3 rows, 1, 2, 3. So now I'll create X is equal to 1, 2, 3 and Y is equal to 1, 2, 3. Okay. Now, what do I want to do in order to access these particular values so that I can multiply the exact delta I comma delta. So I have to multiply the proper gradient value with the proper location, correct? So now since we are stacking it like this, what I'll do is I'll just multiply again this as many times as we have the widths or as many times as we have the columns. Okay. You will see this straight away, but this does not work for Y. So if I start doing this here, 1, 2, 3, this is not going to work because I'll be accessing. So look at this one. So what will I be accessing? Let me write it this way, which makes it easier for you guys. Okay, so what am I accessing first? It is 1, 1, right? 1, 1 is, so what is 1, 1? We have 1, 1, we have 1 and 7, right? So this works. So we want to multiply delta Ix and delta Iy. So initially we, in the delta I, okay, let me write delta Ix and delta Iy as well, so that delta Ix and delta Iy. Two columns. So I have 1, 2, 3. Sorry. I have 1, 4, 7, 2, 5, 8. 3, 6, 9 and 7, 6, 3, 8, 5, 2. 7, 6, 3, 8, 5, 2. 9, 4, 1. Okay. So you can see that for 1, 1, we are accessing 1, 7. So which is actually right, correct? So at 1, 1, we have 1 and we have 7. But what is the next value that we are accessing? We are accessing 2, 2. Is that right? So 2, 2 is 5 and 5. So do we have 5 and 5 in Ix and Iy? No, we have 4 and 6. So we have 4 here and we have 6 here. It means that essentially we must be accessing 2, 1 and not 2, 2. So we have X to be right because we want to take 2, 1 and not 2, 2. So we have our X location right, but not the Y location. Let's go one more. What is next? We have 7 and 3. 7 and 3 are coming from 3, 1, right? But what do we have? 3, 3. So again, we have got our X to be right, but Y to be wrong. Do you see what is common in all of the Y's? We are taking 1, 1, 2, 2, 2, 1, 3, 1. Then we'll go again 1, 2, 2, 2, 3, 2. So we need to repeat the elements of Y. So initially, what did we have as Y? We had 1, 2, 3, right? So we need to shift this 2 to this one and 3 to here, and we have to repeat the elements here. Okay, so now we'll be accessing 1, 1, 2, 1, 3, 1, 1, 2, 2, 2, 3, 2, 1, 3, 3, 3. And you can see that this will correspond perfectly with each other. Okay. So on and so forth. So that is why what we are going to do is we are going to repeat the X W1 times. Okay, we are trying to stack all the columns into just one column. Okay, so for this, what you need is repetition of a matrix. Okay, this is what we call the rep mat. So MATLAB already has a built-in function to do that for you. So for example, let's say, just write it here. So if you have X is equal to 1, 2, 3, and if I do X is equal to rep mat of X times 3 cross 1, I'll be getting what I desired. So what is essentially happening here? What rep mat does is it just creates a 3 cross 1 matrix that you need. Okay, so we are specifying the size here. Okay, and it will replicate the X so many times. Okay, but what is there in X? We have 1, 2, 3, again 1, 2, 3, and again 1, 2, 3. So this is what we are going to get. In case if you give the size to be 3, 2, what will happen? You will just get X repeated 3 by 2 times, and for each X just replace 1, 2, 3. Okay, that is what is going to happen. Okay, so now we have created this part of the X. Now we have to create Y, right? So we have to repeat the element and not the matrix itself. Fortunately, we have a MATLAB built-in function for that as well. And we are going to use rep element, okay, rep element. So whenever you give repetition of element inside a matrix, so it's very simple. So if you have Y to be equal to, again, 1, 2, 3, and if I give Y is equal to rep element of Y, 3 times, it means that each element will be repeated 3 times. And that is the output that I'm going to get. Okay, as simple as that. Okay, so now we have created X, all the X's, all the Y's. Now we have to create the entire rows, right? So what we want here is, let me just take this X off. Just take this X and Y off. Okay, so we need zeros in between them, right? We are essentially trying to create a matrix. We need zeros between them. We need zeros after them. And we need ones. And again, we need zeros, right? So by now, you should already understand that the number of elements in this vector, column vector, is W times H. So what we are going to do is, let's get back to the code. Create a column vector of zeros of length W times H. Create a column vector of rows. And then we are going to stack all our X and Y's in zeros and ones, like so. Okay, so this you have already seen in the lecture. You have row 1 and row 2. Okay, so this is the row 1 of Jacobian. Understand that this X is again a huge matrix. It's a huge column vector of length W times H. we have so many number of zeros, we have so many number of y's, we have so many number of zeros again, ones and zeros again. Okay, so we are going to stack this. So once you create the x, y's and zeros and ones, you just have to stack them up. And then for the final Jacobian, we have to create a concatenation of row 1 and row 2, but we are going to do it in the third dimension. Okay, so what do I mean by doing it in the third dimension is, so since you already have x to be a column vector, and next you have zeros, and next you have all the y's, and next you have all the zeros, and next you have all the ones, and next you have all the zeros, right? So now this itself has become an image, right? So now you have w times h times 6 is the dimension of this particular image. Okay, I'm just calling it an image just for your understanding. So now we are already into 2 dimensions, right? You cannot have it. I mean, you cannot add any more into this dimension. You are already filled with 2 dimensions. So the only thing left is the third dimension that we have. So we are going to stack the second row behind this image. Okay, we are going to stack it behind this image. So now row 1 corresponds to the image that is in front, the layer 1, if you will. Okay, and we are going to put the row 2 in the second layer, because row 2 again is an image, is again an image of size w cross h into 6. Okay, so we are going to put it behind it. Okay, so now the Jacobian is a matrix. So let's finally understand what Jacobian is. Okay, now Jacobian is a huge matrix with w times h length. Okay, that is, this length is w times h. Okay, comma, or into, we have 6 columns in each image, in each layer of Jacobian, and we have 2 such rows or 2 such images. So this is the total, this is the dimension of your Jacobian. So when you write this function and when you get the output, you must make sure that the dimension of the matrix that you're outputting is of size mentioned so. Okay, so this is the ugliest part of the project, and after this it's pretty simple, right? So now it's simple. So what do we have? Okay, we are out of Jacobian. Okay, we are back to line 63 after maybe half an hour, I don't know. Yeah, so J here is 63, and next what do we want to do? So what is in line 65 and 66? Let me write that down as so in line 65. Okay, line 65, we are doing delta ix times dou w x by dou p. Okay, and line 66, what we are doing is delta iy times dou w y by dou p. All right, so how do we access? So you know that you know how to access dou ix and dou iy if you simply so we know that we concatenated them together, right? So that is what we did it in. So we already have that. Where do we have it from? So we have already found out what is our gradient from line 16, right? So line 16 already has found out delta ix and delta iy. Make sure that you vectorize it by taking the column. So it means that if you have found out this, then I want you guys to do this. Okay, so put it as one single column. So this is a column vector. And how do you access dou wx by dou p from the Jacobian? So now you know that Jacobian has, let's say, w times h number of columns, or sorry, rows into 6 columns into 2 rows, right? So how do I access X? That is the first row. So I want Jacobian. Obviously I want all the rows. I want all the columns, correct? I want all the 6 columns. But for X, I know that row 1 is the first image, that is in the first dimension. So I want J of all comma 1. Similarly, for the Y, we go to the second image, second layer, and get the second column out, or the second layer out. So let's again make sure that our dimensions are right. Okay, so what is the dimension of delta X, delta IX? So we have width comma height cross 2. And what do we have in Jacobian? Dou Wx by dou P. What is the dimension that we have? Since this is layer 1, we have, it's an image of size, how much? W cross H cross 6. Okay. And remember that, okay, so now I want to show one last part of multiplication here. So let's say delta Ix into delta Iy into, let's say x0, y0, 1, 0, 0, x0, y0, 1. Okay, so how do you do this? So you do delta Ix into x plus 0 times delta Iy, right? So this is I plus, so basically these two into this column, then into this column, and then into this column, so on and so forth, right? Delta Ix into 0 plus delta Iy into x plus delta Ix into y plus delta Iy into 0, and so on and so forth. So you get where I'm coming from, right? Let's look at this from another way. Let me just multiply all the delta Ix with the first row. Okay, so that is nothing but delta Ix into x, delta Iy into, delta Ix again, delta Ix into 0, and delta Ix into y, and delta Ix into 0 again. Okay, and delta Ix into 1, and delta Ix into 0. Similarly, I can multiply the delta Iy with all the second row. So I can have delta Iy into 0, delta Iy into x, delta Iy into 0 again, delta Iy into y again, and delta Iy into 0, and delta Iy into 1. Right? Now, I can add this up. Right? And I still get the same answer. So you can see that what did I get here? Delta Ix into x plus delta Iy into 0 is 0. You understand where I'm getting, right? Delta Ix into delta y into x, because the first element is 0, and so on and so forth. So you get the idea where I'm coming. So basically, we are trying to find the dot product of delta I into dou w by dou p, Jacobian. So in order to vectorize it, we just do this line 65 and 66. We initially multiply all the Ix with the first row of Jacobian. We multiply all the delta Iy with the second row of Jacobian, and then we just add it to find the A. Okay, so line 65, this is line 65. Okay, I'm just writing it here. And this is line 66 here, what we're doing. And in between them is line 68. That is the addition process. Okay. We are doing all this for just one reason, is to vectorize the entire multiplication process. If you start looping through each and every pixel, trust me, even if you finish your exam on December 10th and your finals on December 18th and you go back home, still the program will be running. So don't do that. Okay. So this is how we have to do it if you want immediate results. And from now on, so with this in line 68, you have already got the A, right? We have the A matrix. Once A is found, it is very straightforward. Find the Hessian, which is A transpose A, and find the delta P, which is H inverse of A transpose into P. And as I mentioned earlier, B is the error that is coming from line 44. Please go back and check it. And update P with the delta P. And it's always a good idea, to print the state. So let me tell one thing. Printing statements always will reduce the speed of the code, but in order to debug, these are very helpful. So when you're writing the code, just print what is the number of iterations that you have run until now, and what is the value of the P. So based on that output, you can actually set the threshold for P and items. So you just have to print the statement if you want it. So we have updated the P and we end the loop here. Okay, so the iterative alignment procedure ends here. And at last, we update U and V from P5 and P6, which will go out as your outputs. All right, and then once it goes back, everything else is done for you. So you update the X1, Y1, and the loop just continues. Okay, so these are the things that you need to do. I hope I have made myself clear. I know it's very tedious to follow this particular project, this particular line of thought. It's always a little ugly when Jacobian, when calculus comes into picture. So this is what you have to do for this project. Unfortunately, we have made the MB tracker as extra credits. And it's very much similar to this one. Once you have understood this part, going to that part shouldn't be easy. So if you guys have any doubts on MB tracker, and if you want to do that, you can always come to our offices and then ask the doubts you have. Okay, so that's it. I'll stop the recording here. Thank you.